Good morning everyone. I am Uddhavara Sandeep Pawar and today I am presenting you my project on real-time EV ADAS dashboard using STM32 Blue Pill, PicsimLab and Python. The project combines embedded system, electric vehicle simulation, ADAS features, UART communication and Python visualization into one complete system. The main objective of this project is to monitor vehicle parameters in real time while providing safety features like collision warning, blind spot detection, parking assistance, and fault monitoring. In modern electric vehicles, hundreds of UV sensors are generated every second. It becomes difficult for the drivers or engineers to monitor all these parameters simultaneously. Without proper monitoring the system, uh, we may face many problems such as motor overheating get unnoticed, battery level may become critical, or collision risk may not be detected in time. So, the solution for this problem, we have developed a system that provides real-time vehicle monitoring, ADAS safety features, live Python dashboard, motor fault detection, alarm system, different drive modes, and this allows operators to monitor the entire vehicle from a single dashboard. So, the system architecture overview. This slide shows the complete architecture of our project. The process starts with sensor. We have used 4 potentiometers inside the PicsimLab to simulate one for acceleration, one for brake, one for SOC, one for motor temperature, and these inputs are ready by the STM32 Blue Pill. The STM32 processes all calculations such as speed, torque, battery SOC, ADAS logic, alarms. After processing, the STM32 sends telemetry data through UART at 115200 baud rate and it displays it on the dashboard in real time. So the overall flow of this project is sensor, then STM32, then UART and then Python dashboard. Our project was completed in 9 phases. The first phase was development environment, the second phase was GPIO and peripherals, the third phase was ADC sensor inputs, the fourth phase was EV dynamic model, fifth was ultrasonic ADAS, sixth was fault and alarm system, seventh was UART telemetry, eighth was UART shell, and ninth and the last one was Python dashboard. The phase 1 and 2, which is setup and configuration, the STM32 cannot directly. Uh, so, in this phase, our project was completed in 9 phase. Uh, Phase 1 and 2. In phase 1, we prepared our development environment. We use first STM32 Cube IDE for embedded programming, then PicsimLab for simulation, Python for dashboard development, Matplotlib for real-time graphs. In phase 2, next we configured STM32 peripheral. This includes GPIO, ADC, timer interrupt, PWM for buzzers, and UART for communication. In the next phase, which is 3 and 4, we have done data equitization and simulation. The STM32 cannot directly understand analog voltages, so we use the 12-bit ADC. The ADC converts voltages between 0 and 3.3 volt into digital values from 0 to 4095. So we have connected pins PA0, PA1 and PA2. The PA0 reads acceleration input, PA1 reads brake position, PA2 monitors motor temperature. Using these sensors, Using these sensor values, the STM32 calculates vehicle speed, motor torque, SOC, regenerative braking, remaining range, and drive mode. In phase 5, we have ultrasonic ADAS engine. This phase implements ADAS, which is Advanced Driver Assistance System. We use ultrasonic sensor to detect nearby obstacles. The main features are front collision warning. It alerts the driver if an object is less than 1.5 meter away. Then blind spot detection. It checks vehicle on the left and right side. Then time to collision. Instead of only measuring distance, it predicts how much time remains before the impact. And at last, we have done parking assistance system. It warns the driver if an obstacle is within 30 centimeters while parking. These features improves vehicle safety. So next, we have fault detection. To improve reliability, we implemented a fault detection system. The STM32 continuously checks motor temperature, battery level, sensor failures, communication errors, and collision condition. If any fault occurs, a corresponding bit is set in a fault register. We also implemented four alarm levels, which are alarm none, then alarm advisory, then alarm warning, then alarm critical. Then the next slide is UART telemetry. After processing all information, the STM32 sends telemetry data through UART. This data includes speed, SOC, motor torque, motor temperature, range, acceleration, position, brake position, ultrasonic distance, collision status, blind spot detection, alarm level, and all this data is received serially by the Python dashboard, and it updates continuously. So the next slide is UART shell. To make debugging easier, we develop a UART shell. Instead of modifying firmware every time, we can directly send commands. For example, change the vehicle speed, change battery SOC, increase motor temperature, switch eco and sports mode. So this reduces the testing time. So we have implemented the UART shell here. In the last phase, we have developed Python Matplotlib dashboard. The dashboard is developed using Python and Matplotlib. It consists of five panels. First is speedometer, which shows the current speed. Then SOC, a battery SOC indicator, speed history graph, and an EV information panel showing temperature, torque, range. And we have also built a bird's eye ADAS view displaying nearby obstacle around vehicles. The dashboard updates continuously using the UART data lively. So here is the project workflow from sensor to dashboard. So first we have read ADC, then we have EV updated, then ADAS updated, then we have triggered HCSR04, then we captured the return ultrasonic signals, then we computed TTC, which is time to collision, then FCW, which is front collision warning, then BSD, which is blind spot detection. Then we have set the alarm, which is advisory, none, warning, and critical. Then we drive LED buzzer. Then we have built UART frame. Then we have sent it via USART1, which is UART1, and then it the live data is generated to the Python dashboard. So at last we have got the result. We have got the inputs, we have got the outputs, which are real-time speed and SOC, then ADAS collision detection, then we have monitor blind spot, then we have motor over temperature fall, then we have verified UART shell, and at last we have Python dashboard live. So thank you everyone. This was the end of the our presentation. Thank you. So we are just moving towards our next part, which is a project demo. So I am just opening the virtual serial port emulator, which is VSP, and I have connected COM1 and COM4 here, and I will just open the PicsimLab, and you can see it is a data which I am getting. So just I just uploaded my binary file here. We have used Blue Pill board here. Then just a minute, I will just open. Yes, I am getting the live data here. You can see it is updating the data every minute. So let me just go to the command prompt. So I'm just opening the command prompt. Okay, and I'm just pasting my path of the file. Yes, I've got my dashboard here, and just a minute, I will get here all the received data from my PicsimLab to Python dashboard. So let me just open my EV dashboard on the one side. Okay, you can see it is updating live. So just a minute, I will just open it, open the virtual term. I will just show you the demo. Yes, you can see on the left side I have my Python dashboard and it is updating live, and at the right side I have my virtual IO term in a PicsimLab. So as you can see, my speed is 38, here 40. I am just increasing my speeds slowly and it is become 41. Yes, my SOC is 99, which is here. My back pedal is 0 here, and as I increase my back pedal, it is also increasing. You can see it has become now 68. My motor temperature is 35.9 degrees Celsius. So as I increase my motor temperature, it is now becoming, yes, you can see this 73.8 degrees Celsius. So yes, these are the 4 potentiometer I have used, and here are the 3 ultrasonic sensor. One for his front, one for his right, one for left, one for his left, and one for his right. So you can see as I just press the pedal downward, then it is giving me the critical warning, which is a front collision warning near the obstacle. Our vehicle is near the obstacle, and as we pull up this, then it is giving me the normal. The vehicle is in the normal condition. As I am pulling down the left pedal, left, which is used for blind spot detection. You can see, yes, it is giving me the advisory, which is blind spot detection advisory, which is 5 centimeter away. You can see it is giving me the alarm advisory, and as I move down this right, then it is giving me the right side blind spot detection, which is 9 centimeter, and the alarm is here and now advisory. This is 98.9 centimeter, 98 percentile. Uh, we have used ADAS bird eye view for this. So this is the speedometer of our vehicle. This is the SOC, which is battery SOC, state of charge, how much our battery has left. We can see here. Then how much kilometers we have, the battery can be run. This is the kilometer express here. Then the vehicle is running in the normal mode as shown here. Then these are the EV metrics, which consist of torque, acceleration, brake, motor temperature, alarm, fault, and signals. And this is ADAS bird eye view, which shows the front vehicle, left vehicle, and right vehicle. This is the front collision warning, which gives front collision warning. This is blind spot detection left, and this is blind spot detection right. So this is TTC, which is time to collision, which is 99.9 seconds. Here speed is 32 kilometer per hour, and this is the speed history. How much speed is increased, how much speed is decreased. We can see here how much the speed has increased now and decreased now. We can show the speed is decreasing. So it gives us live data. This is my overall project. This is my overall project, and uh, at last, before I conclude, I would like to express my sincere gratitude to my internship mentors and guides for providing me with this valuable opportunity to work on the real-time EV dashboard project. And this internship helped me again gain a practical experience in embedded system, STM32 programming, UART communication, ADAS concepts, and Python-based dashboard development. The guidance and support and knowledge shared throughout this journey have greatly contributed to my technical and professional growth. I would like to thank everyone who supported me during the successful completion of this project, and this is my overall project. Thank you everyone for this wonderful opportunity. Thank you.